Hello and welcome. In this video, we're going to be looking at a very important topic in the study of calculus on multivariable functions. We're going to be looking at the derivative, or what we call the partial derivative of a multivariable function with respect to one of the variables. And we've already got the building blocks from a previous video. We took a look at limits and continuity. Now we can define what this partial derivative is. And it may just kind of help to refresh our memory on what we defined as the derivative of a single variable function first. So in single variable calculus, where we just have a function y equals f of x, if we think about the derivative as representing the slope of a tangent line at a point P, well, we calculated that slope by looking at the slope of a secant line here in green between the points P and Q. That's pretty simple to calculate. If point P is at an x-coordinate of a, then we just let Q be at an x-coordinate of a plus h, where h could be negative if we wanted Q to be left of the point P. And we can calculate those two y values and essentially calculate slope of the difference in the y values over the difference in the x values. And to get the slope of the red tangent line, we take the limit as h approaches 0. We have a couple notations for that particular value. That would be defined as f prime of a, the derivative evaluated at x equals a, or we might say dy by dx. That is another way to represent our derivative, and then we could use a vertical bar and evaluate at x equals a if we like. That's another notation. Now, the problem with multivariable functions, if we have a function, let's say z equals f of x, y, or potentially u equals a function of n variables, well, this means that we don't really just have a left and a right direction. We could be talking about the change of z in any direction along the xy plane, or we could talk about a change in u in any direction in n-dimensional space. So slope could be really in as many directions as we want. The aim of a partial derivative is to take a function, let's say z equals y squared minus 2x. And if we wanted to try to graph that, well, that would be parabolic along the yz plane and any cross sections parallel to it. It would be linear in the xz plane and any cross sections parallel to that. So you can kind of get a general sense of it. The aim here of our partial derivative is to find out whether or not z is increasing specifically just in the direction of positive x, and whether or not z is increasing or decreasing in the direction of positive y at any given point on the surface. Why don't we pick a point on the surface and think about what slope might mean in the direction of positive x and positive y. Let's pick the point xy equals 1, 2. And if you plug that into the function, you'll find that z is equal to 2. On our graph here, that would be 1 unit forward in the x direction and 2 units forward in the y direction, and giving us 2 units up in the z direction. So maybe it's a point right here somewhere on the surface. If we go in the x direction, you might be able to see from this picture that hopefully we see it's decreasing in the direction of positive x. If we're looking in the positive y direction though, looking at these blue cross sections, it looks like it should be increasing. Let's see if we can calculate those slopes. And again, we're going to use limits just like we did in single variable calculus. From that point at 1, 2, 2, what if we take a small step forward just parallel to the x-axis? Now, we could be taking a small step forward or backwards, and we can obtain a second point on the surface and figure out the slope between those 2 points, just like we did with single variable functions. What we'll do is we'll let our initial point xy be 1, 2, and our z value at that point would be denoted by f of 1, 2, which we already have calculated is equal to 2. Now from there, we'll take a small step parallel to the x-axis. In this case, we would have x change from 1 to 1 plus h, where h could be positive or negative. But since we're moving parallel to the x-axis, our y-coordinate will not change whatsoever. If we look back at the surface, essentially we are traveling either forward along the x-axis or backwards along the x-axis, and we would stay at a y value of 2. But we're kind of curious as to what z is going to do. The z coordinate at that point where x is equal to 1 plus h and y was equal to 2 would be denoted as f of 1 plus h comma 2. Okay, well, from those 2 points now, we can calculate slope. And you can still think about slope as essentially being rise over run. In this case, it's going to be a change of z, height above the xy plane, with respect to a change of x, parallel to the x-axis. And we'll take a difference of z values, f of 1 plus h comma 2, minus f of 1 comma 2, and a difference in x values, 1 plus h minus 1. And that will simplify so that in the denominator we simply just get h. And this is our difference quotient. This is going to be the slope between 2 points on the surface, just like we're finding the slope of a secant line. Now, if we want to actually get the slope at a point, we will let h approach 0. As h approaches 0, we call this the instantaneous rate of change of z with respect to x. And we can go ahead and calculate that from knowing what this function is. We know that the function f of xy is equal to y squared minus 2x. So we should be able to actually try evaluating this limit. The limit of f of 1 plus h comma 2 minus f of 1 comma 2 all over h as h approaches 0. And we can evaluate the numerator by simply plugging in x as 1 plus h and y as 2. And we already know that f of 1 comma 2 is simply a z value of 2. From here, we can expand out the numerator, collect terms, and we see that we have 4 minus 2 minus 2h minus 2 again. And all of these constants cancel out. And h's can cancel out after that, leaving us simply with minus 2. This is telling us that along the x-axis, we have a decreasing z value. Let's see what that means by looking back at the picture here. That means from this given green point, every 1 unit forward along the x-axis, we are dropping by 2 units. Or at least at that point, we have a slope of negative 2 in the positive x direction. Now remember, in the positive y direction, we can see these blue cross sections. It looks like we should probably be increasing. And that rate of change in the direction of y is not always going to be constant because we have parabolic cross sections. Let's try taking a small step parallel to the y-axis now and look at what we get for the rate of change of z with respect to y. If we wish to take a small step parallel to the y-axis, then we're going to be taking our initial point 1 comma 2 with the z value corresponding to f of 1 comma 2 and moving to a new point 1 comma 2 plus h. H could be positive or negative. We just need a second point nearby, and our z value at that point would be f of 1 comma 2 plus h. And we get a very similar looking slope formula here. The slope between those 2 points would simply be a change of z, this time over a change in y. And so we have our difference in z values over our difference in y values, and the 2's cancel in the denominator, leaving us just with h. Now that will just get us the slope between 2 points, which is like an average rate of change of z over an interval of y. If we want to get the instantaneous rate of change of z with respect to y, then we let h approach 0. And we can try evaluating this limit as well. Here we've got the limit of f of 1 comma 2 plus h minus f of 1 comma 2 all over h as h goes to 0. Once again, our function is y squared minus 2x, so we'll just plug in those values for y and for x, and that will give us this expression 2 plus h all squared minus 2 times 1 all minus 2, since we know that f of 1 comma 2 is a z value of 2. And we can expand that out, expanding the square, and we can see we have 4 minus 2 minus 2. All of the constants cancel out nicely. And then we have a common factor of h that we can pull out of the numerator and cancel with h in the denominator. Well, that cancels the denominator completely and just leaves us with the limit of 4 plus h as h approaches 0, and that's easy to evaluate. That will just give us 4. And that corresponds to looking at the picture again. At that particular star value, if we are going in the positive y direction, our z value is increasing with a slope of 4. Now, what we've just done here is what we call the partial derivatives of f with respect to x and the partial derivative of f with respect to y. So now why don't we give formal definitions for what a partial derivative is? And of course, just like with single variable calculus, there are a couple different notations you can choose from. Let's suppose that we have some sort of function of x and y. And oftentimes we'll let z equal the output of that function. If we want to just use function notation, then the partial derivative of f with respect to x is defined as the limit of f of x plus h comma y minus f of x comma y all over h as h goes to 0, assuming that limit exists. And when we calculate this expression, we get a new function of x and y. So the partial derivative of a function is a function itself. This is just at an arbitrary x and y in the domain of the function, and it is not necessarily always going to exist. We do see that we have problems with continuity on functions of multiple variables, so we can also get problems with differentiability of functions of multiple variables too. Similarly, the partial derivative of f with respect to y is the limit of f of x comma y plus h minus f of x comma y all over h as h goes to 0, again, assuming that that limit exists. It is possible that a function is not differentiable, but if both of these limits exist, then we say that the function f is fully differentiable. Now, like I said, there are some other notations, even with single variable calculus. Sometimes we use f prime or y prime notation. F prime is really handy if you want to continue using function notation, and f prime of 5 is convenient so that you know you're taking the derivative of a function and plugging in x equals 5. But especially if we have an equation and it can't be expressed as a function, but we still want to find the rate of change of one quantity with respect to another, we often use Leibniz notation and write dy by dx. And that tells us that we're looking as y changes with respect to x. We have a similar sort of notation here with partial derivatives as well. For the partial derivative of f with respect to x, we can use this f sub x notation. Sometimes I'll just say that's fx of x comma y, or I'll say f partial x of x comma y. But we can also say that if z is a quantity dependent on x and y, we might write the partial derivative of z with respect to x. And you notice that I'm not using a typical d here. I'm using a little scripted d. We tend to say that this is del z del x rather than dz dx. And you may also just pronounce this as partial z with respect to x, depending on how you want to verbally say this notation. Similarly, we could say the partial derivative of f with respect to x, or del f del x. Even less common, at least I probably won't use this notation, is we use capital D as a differentiation operator with a little subscript x and apply it to the function f. And you might see that notation as well. Now, as far as the partial derivative of f with respect to y, we may use this fy notation with a little subscript y, or if we wish to treat z as a function of x and y, then we might think of partial z with respect to y, or del z del y. We could also look at del f del y, or use the differentiation operator d sub y of the function f. And these are also quite handy notations. We can use this sort of Leibniz notation much more often when we don't have a function, but we still want to talk about the rate of change of one quantity, z, with respect to x or with respect to y. Just notice the difference between a single variable function, dy by dx, versus a function of multiple variables, del z, del x. That's a dead giveaway for whether or not y depends on multiple variables, in which case here you can see it doesn't, or whether z depends on multiple variables, and in this case you can see it does. Now, of course, if you remember in single variable calculus, we don't use the limit definition of the derivative for very long. We can try calculating a few derivatives of common functions and find out that there are plenty of standardized rules for differentiating common functions. And all of those rules are still going to apply here. So we don't really have to reinvent them again. The one change that we have is if we are only wanting the partial derivative of a quantity with respect to one variable, that means that we are going to treat the other variables as constants. So let's try applying that to an example here. Suppose our function f of x comma y is equal to e to the x sine of 2y plus x squared over y. Let's calculate the partial derivatives with respect to both x and y separately, but let's do this process with a little more efficiency rather than using the limit definition. If we want to compute the partial derivative of f with respect to x, then we just treat y as a constant, and we follow all of the rules of derivatives that we learned already from single variable calculus. So this notation, partial f with respect to x, well, that means that we are going to be taking a look at the derivative of the expression on the right. We use del by del x as an operator, that is, taking the partial derivative of some expression with respect to x. So we are going to be taking a look at the expression e to the x sine 2y plus x squared over y. Now, rules of derivatives still hold out here, so that means that we can take that partial differentiation operator and apply it to each term individually using the sum rule for derivatives. So we'll take the partial derivative with respect to x of e to the x sine 2y, and we'll take the partial derivative with respect to x of x squared over y. Now remember, we're treating y as a constant. If y is just some number, then sine of 2y is just some number, and all of that is a constant, and we can apply the constant multiple rule to that first term. Sine of 2y is a constant, and we'll just take the partial derivative of e to the x with respect to x. Over in the second term, this y is a constant, and so we can actually pull a constant of 1 over y out of that term, and then just apply the differentiation operator to x squared. And it's at this point in time that we can finally just apply our power rule and exponential rule from single variable calculus. The derivative of e to the x with respect to x is e to the x, and the derivative of x squared with respect to x is 2x. And I'll just write this usually with exponentials in front of trigonometric functions since it's a little bit more convenient to read that way. So maybe you can get a little bit quicker with this process now to just compute the partial derivative of f with respect to y. Just remember, we're keeping x as a constant. We can probably simply just jump right to this partial derivative. If x is a constant in this first term, then e to the x is a constant. We just need to take the derivative of sine 2y, and you have to remember to use the chain rule there. The derivative of sine of 2y would be cosine of 2y, but we have to multiply by the derivative of 2y, and that gives us 2e to the x cosine 2y. Now in our second term, this x squared is simply a constant. We'll need to take the derivative of 1 over y, which is the same thing as thinking about the derivative of y to the minus 1, and that would give us negative 1 over y squared. Putting the x squared back in as this constant multiple gives us negative x squared over y squared. Now, the idea of a partial derivative doesn't just stop at functions of two variables. If we have a function of several variables, let's say we have a function f, which is dependent on variables x1, x2, all the way up to xn, then the partial derivative of f with respect to the variable xi, this would be the limit as h approaches 0 of f evaluated at x1, x2, all the way up to xn, with the one exception that we have xi plus h. And then we subtract f evaluated at x1, x2, all the way up to xn. So really, we're still treating x1, x2, all the way up to xn as constants, except for the one variable that we are differentiating with respect to. So luckily, the idea of a partial derivative doesn't really get more difficult the more variables you throw in. In fact, it just essentially allows you to treat even more things in the function as constant. We're only going to be looking at varying one of the variables and seeing what happens to the change in the overall quantity. And then you get to apply all of the rules we're already familiar with from single variable calculus. Here's a quantity that depends on three variables. I've got v equal to pi times h times r1 squared minus r2 squared. If you want to know what that equation is actually for, it's to calculate the volume of a hollow cylinder, a hollow circular cylinder. We've got two radiuses. We've got an outer radius and an inner radius, and the height of this cylinder. And this will calculate the volume of that solid. Now, we can take a look at how V changes with respect to H. In this case, it would probably be better to use Leibniz notation, del V by del H. And I'm using that simply because I haven't used function notation yet at all. I haven't written V as a function of R1, R2, and H. So I'll use Leibniz notation. And here we're going to be treating R1 and R2 as constants. And of course, pi is always just a mathematical constant. Now, remember, if R1 is constant and R2 is constant, then this whole factor of R1 squared minus R2 squared is constant. Pi is constant. So it's just a bunch of constants all multiplied by H. And the partial derivative of V with respect to H would simply just be pi times R1 squared minus R2 squared. Pretty straightforward. That's just a linear function with respect to H. And you notice that as H is increasing, that the volume is increasing, assuming, of course, that R1 is larger than R2. That should hopefully make sense. And it doesn't matter what H currently is, the rate of change of volume with respect to H is a constant. This partial derivative doesn't depend on the current value of the height of this cylinder. Well, now let's take a look at the partial derivative of volume with respect to R1. So this will be del V by del R1. Here we're going to be treating H as a constant. Of course, pi is a mathematical constant. R2 is also a constant. Now what you could do, if you like, is actually maybe just write out this same volume equation but expand it out. This will give us V equals pi h R1 squared minus pi h R2 squared. But if we're treating H and R2 as constants, then this second term here has a derivative equal to 0, since it is entirely a constant. And we only need to apply the power rule to the first term on R1, because pi and h are constants. This gives the partial derivative of volume with respect to the outer radius as 2 pi h times R1, the outer radius. Now you'll notice h is going to be a positive value, and so since R1 is also a positive value, as R1 is increasing, we see that volume is increasing, which should hopefully make sense. As the outer radius gets larger, we see that volume should be increasing. But it is not increasing at a constant rate. You can see from this partial derivative that the rate of increase of volume with respect to the outer radius depends on the outer radius. So it's non-linear. Now last but not least, we can calculate the partial derivative of volume with respect to the inner radius. And it's very, very similar. We end up with negative 2 pi h R2. Of course, that also depends on the value of R2. Hopefully this makes sense as to why we have a negative sign. For any particular value of R1, R2, and H, if R2 starts to increase, we end up having a decrease in volume. That's because the hole in the middle of this cylinder is getting larger. Now, notice how I've worded this question. I've said to compute all first partial derivatives. These are all order 1 derivatives. We've only differentiated with respect to one variable once. But just like with single variable calculus, we can look at second derivatives. Here we can look at second order partial derivatives as well. And of course, let's see what kind of notation we'd have to use for that. For higher derivatives, we already have kind of two major competing notations. We can use function partial derivative notation, or we may choose to use Leibniz notation. It might be best to make a little chart here. Depending on which of the first order partial derivatives we're given, and depending on which of the variables we want to differentiate with a second time, we have different kinds of notations. Now, function partial notation is pretty easy to follow. If we have the first partial derivative of f with respect to x, and we differentiate with x a second time, well, we just add a second subscript, fxx, evaluated at x comma y. And if we have the first partial derivative of f with respect to x, and now we want to differentiate with respect to y, we'll just have fxy evaluated at x comma y. So basically, we're just adding a second subscript on and the order of differentiation is from left to right. And this is the same thing if we want to start with the partial derivative of f with respect to y, and then differentiate a second time with respect to x or y. Differentiating with respect to x twice and y twice, it's not really hard to confuse that, but these two derivatives where we have xy or yx, those are what we call mixed partial derivatives. Now, where the confusion can arise a little bit between the two different notations is the order of those mixed second order partial derivatives. Now, let's take a look at Leibniz notation and see how we can use the differentiation operator to kind of come up with how we can notate the second partial derivative of z with respect to x and y combinations. Here we'll apply the partial differentiation operator with respect to x to the first partial derivative of z with respect to x. And you can kind of see how we might come up with a notation here. The notation that we arrive at is del squared z, that's the second partial derivative of z, and in the denominator we have del x squared. So that's with respect to x twice. As for the mixed second order partial derivative though, we're going to apply the partial derivative operator with respect to y onto the partial derivative of z with respect to x. And notice the order of adding the differentiation operator in front of the first derivative. In this case, we have del squared z, which is the second partial derivative of z, with respect to, and then in the denominator, we have del y del x. And that is a little confusing. Our first derivative was with respect to x, and our second derivative was with respect to y. It does make sense to write it in this order because operationally, we're actually adding in the partial differentiation operator in front of the first derivative. If we're going to apply that same strategy of differentiating the partial derivative of z with respect to y, then we end up with del squared z by del x del y as the second partial derivative of z with respect to y first, x second, and then we'll have del squared z by del y squared, which is the second partial derivative of z with respect to y twice. So you do have to be very careful. You notice that the mixed second order partial derivatives read backwards from each other in these two notations. Function partial derivative notation is reading from left to right. Leibniz notation is reading from right to left in the denominator. And that makes a lot of sense if you understand where these two different notations come from. Now, if you think that's going to be very confusing, and of course, maybe you want to just stick to one notation or the other, I have some very good news for you. There's a very important theorem coming up here which allows you to change the order of partial derivatives, meaning that those mixed partial derivatives for second order or even higher, the order really doesn't matter so much. But you do have to be careful about what criteria the function has to obey in order to apply this theorem. Here we can take a look at Clairaut's theorem. And Clairaut's theorem says that if we have a function of, let's say, two variables, although this can be applied to functions of many variables, let's say that that function is defined over an open subset D of R2. Basically, just imagine that it's defined over some sort of disk, but not necessarily including the boundary. Let's suppose that these two mixed second order partial derivatives, fxy and fyx, exist. And here's the kicker, they have to be continuous on that region. So this works well for functions where you know you can take the second derivative and you end up with a well-behaved function. Now, with that criteria in mind, then the two second order mixed partial derivatives are equal to each other for every single point in that region D. What this means for us is that if we have a really nice function, such as maybe just a polynomial or trig function or exponential function, with the exception of a few functions we've taken a look at, a lot of the time our second partial derivatives are continuous. They are very nicely behaved functions, in which case that means that the second order mixed partial derivatives are equal to each other. You can just replace one with the other, and the order doesn't really matter. But as you can probably imagine, the conclusion of Clairaut's theorem is very, very important for most of the functions we're talking about, since a lot of functions we look at do have continuous second order partial derivatives. Now, if you remember in single variable calculus, the moment that we were able to differentiate several common functions, we started turning our attention to equations in terms of two variables. And that will at least still represent some sort of relationship between, let's say, y and x. If we want to figure out how y changes with respect to x, though, we have to use a technique called implicit differentiation. And we have the same kind of strategy here for equations of multiple variables as well. It's a relationship between, let's say, x, y, and z. We want to know how z changes with respect to x, and we'll apply the partial differentiation operator with respect to x to both sides of the equation. Or maybe we have something where pressure depends on temperature and volume, and that would be an equation relating those three quantities. Well, we could take a look at the rate of change of volume with respect to temperature, or look at the rate of change of temperature with respect to pressure. Again, we could use implicit differentiation techniques for that. I'll save that for a future video though, because there are a couple different new strategies for dealing with those kind of relationships that we'll see in future videos. For the time being though, I want to end off by showing you a little visualization about what a partial derivative might look like, at least on a function of two variables. We can visualize that as a surface this way. Now, I'm going to make sure I can do some 3D plotting here, so I'll have with plots. And I may have gone a little overboard with all of the things I'm going to try plotting on here. But let me just explain briefly that we're going to be taking a look at the elliptic paraboloid z equals 9 minus x squared minus y squared. And we're going to be looking at the partial derivatives of z with respect to x and y at the point 1, negative 2, 4. So let me put all of these plots together into one display, and let's see if we can make sense of it. Here is the elliptic paraboloid. And if I take a look around at a y value of negative 2 and an x value of 1, I have this little green point right there. Now, if I want to take a look at the partial derivative of z with respect to x, what I want to do is I want to fix y to be just negative 2. That is actually all of the points on this blue plane that I've plotted, y equal negative 2. So let me orient this so we're looking straight on at that blue plane from the side, and you can see the x-axis along the bottom here. And at that point, if we just were to take a slice out of the surface, you can see it has a parabolic shape opening downward. And we could imagine that this blue line is simply tangent to one of these little cross sections of the curve. And we can see the slope of that line. Now that line just happens to have a slope of minus 2. I've actually plotted a line going through the point 1, negative 2, 4, and every time that x increases by 1, if t goes up by 1, then z has to go down by 2. That's where I get this minus 2t. But y is going to stay constant on that line at negative 2. So there's actually the equation of a tangent line to a curve across the surface. And if we want to take a look at the partial derivative of z with respect to y, then I'll orient this so that I see this red plane. This red plane is where x equals 1, and we're keeping that constant. So we'll just take a little slice out of this elliptic paraboloid, and that slice, again, has the shape of a parabola. We're not looking at the blue anymore. At that point there, we can see it seems to be increasing in the direction of the positive y-axis. And that red line there just happens to have a slope of 4, which is why I've plotted this red line going through the point 1, negative 2, 4, and every time that y increases by 1, I have this plus t. Z has to increase by 4, so I have this plus 4t. That gives you those two little partial derivatives. It's the slope of this blue line going down in the direction of positive x, and the slope of this red line going forward in the direction of positive y. Now, I'll save that torus for later because in order to calculate the partial derivative of z with respect to x and y on the shape of a torus or a donut, we're going to have to know how to use implicit differentiation. So hopefully for now that gives you an idea about what a derivative looks like for a multivariable function. So far, we're really only looking at two directions though. In the positive x direction, how is z changing? The positive y direction, how is z changing? And let's not forget that we don't just have to limit ourselves to x, y, and z. We can look at the rate of change of some function with respect to any variable we want. So stay tuned, we'll take a look at some implicit differentiation and even take a look at how we can create partial differential equations in a future video. And then we have a lot more that we can get into with chain rules and applications. So thanks for watching, and I'll see you in the next video.